Okay, today we're going to take another look at exponential functions. Yesterday we started with the basic one, okay, for an exponential growth or decay, where we have y equals a times the quantity 1 plus b, the quantity raised to the x. Now each of those variables meant something specific. Okay, x and y, we know those are our input and output. Okay, x is input and y is output. Okay, but more specifically, okay, they go very, very close hand in hand. X isn't just input. Okay, when we're talking about exponential growth and decays, we're talking about cycles. Okay, when we talked about half-life and those M&Ms, every time we poured out those M&Ms and took away the ones that were M side up, that was a cycle. That was one cycle. The output was how many we had left. Okay, so the output is the amount remaining or accrued. Okay, at whatever time at whatever cycle we were on. Now A and B, we gave each of those specific definitions yesterday too. We said that what they represented in that equation. What did A represent? You can take a look if you don't take a look at your notes if you don't remember. But what did A represent?
Initial amount.
The starting amount. Okay, whatever the item was that you were measuring, A was the starting amount. And what was B? The percent change. But there's something important about that. Okay, it's really, really important about B. This percent change, Calissa, has to be given to us as a decimal. Okay, on the one problem that we were looking at just a minute ago, where Paul mentioned, shouldn't we use 1 instead of 100? Okay, when you're talking about the percent at the end, that's fine. Okay, you can use the percent exactly as they're given. You can put 50 for 50%. But for B, okay, when we're using in the middle of this formula, for this letter B right here, that has to be as a decimal. We cannot use whole numbers for that. Okay? What are we supposed to be watching out for on B, though? What are we supposed to keep in mind? Say that again? Positive or negative. Okay, keep in mind, could be positive, could be negative. Now, for compound interest, this is a special case. Okay, this is a specific type of exponential growth and decay. This is probably one of the more common ones that you'll see that you'll have to work with in your life. Bank accounts. Okay, bottom line, your bank accounts. So we adapt the equation just a little bit. Now, it's the same kind of idea. You still got some number times a quantity where you got 1 plus something, and it's being raised to an exponent. Okay, it's still the same basic appearance, but there are some minor differences. Okay, A. A is kind of in the same place as what in the old equation? Y. Okay, so we can say it's pretty much the same thing as Y. Now we're talking about money on these, so we can say that it is the amount in the account at time t. Okay, and P is kind of in the same place as what? A. Okay, and A was the starting amount. Anyone know what we call the starting amount in your bank account? It's called the principal. Okay, when you're next year or the next couple of years, when you're, well, probably for the next several years, when you're talking about your student loans, the principal amount is the initial amount that you borrowed. Okay, so loans and bank accounts kind of work the same way as far as interest goes. R. Well, if we're talking about interest, what do you think R represents? Rate. Now, what's important about interest rate? What do you think? It does. Well, the rate stays the same, hopefully. Hopefully the interest rate, well, if it's a bank account growing over time, it'd be nice. But what's important about is What's important about the rate as far as the equation goes? Sorry? It might be compounded monthly. It might be weekly, daily, continuously. That's another slightly different equation. But the key is, guys, it has to be as a decimal. Okay, when we're talking about the interest rate, it has to be given to us as a decimal. Now, n's a little weird, so we'll come back to n. But t, well, what does t usually represent? Time. But the key is time must be given to us in years. So if they give it to you as days, as months, we need to convert that to years. N. N's the kind of goofy one. Okay, it's the compounding cycles per year. Okay, so Nathan mentioned if you have it compounded monthly or you have it compounded daily, we need to know how many times that interest is being compounded per year. Okay? Now, if we look at this formula, guys, they're essentially the same thing. You've got a starting amount. You've got 1 plus something. Now, in this case, B was the steady interest rate, okay, how much you were increasing or decreasing, and X was the cycles, how many cycles it was happening. Well, in this case, kind of the same thing, except this time we have the interest rate over the number of compounding cycles per year. And then in the exponent, we have the number of compounding cycles per year times the number of years. So when we put those together, that just gives us the number of compounding cycles. And this becomes the interest rate per cycle. Okay? So it's really the same formula. It's just adapted for a slightly more specific story. Okay? Now, the key, guys, with any formula, we said anytime you're going to use any formula, you write it down. Okay, so for each one of these stories, we're going to write the same formula again and again, and it's going to help us, number one, memorize it. Number two, it's going to help us know how to substitute and use it. So determine the amount of money in a savings account providing an annual interest rate of 5% compounded monthly if Rick invested $2,000 and left it in the account for 7 years. So we're using the compound interest formula. And anytime we use any formula, we want to start by writing it down. So we'll say A equals P times the quantity, 1 plus R over N raised to the NT. And you guys, I think you said yesterday that most of you are either in physics now or have had physics at some point. When you're working with those equations, when you're working with those formulas, you know you're supposed to list those variables and clearly define them. Well, we're going to be working with similar formulas, so it's very important that we do the exact same thing. Okay, so A is the amount at the end. Well, that's what we're trying to find. P, the principal, the starting amount. Okay, that's Rick's $2,000 that he deposits. R is the annual percentage rate, the interest rate, 5%. But we can't use 5%. We need to change it to 0.05. Okay, N is the number of compounding cycles, how many times it's compounded per year. So it's compounded monthly, okay, so that means compounded 12 times per year. And he's leaving it in the account for 7 years. So now we have all those pieces. Now we can sub them all in. So we'll have A equals 2,000 times 1 plus 0.05 over 12 raised to the 12 times 7. Now, my recommendation, just like yesterday, before we grab those calculators and start pushing buttons, the best thing that you can do is simplify anywhere that you can. Okay, if you can do anything in your head, simplify that part in your head. Okay, and at the very least, we can simplify that exponent in our heads. Okay, and that's going to be 84. Okay, so we got at least a little bit simplified. Okay, now when we type this in the calculator, guys, it's really important that we're doing hitting the keystrokes exactly the order that we need them in. So I'm going to show you guys exactly what to type in here. Okay, 2,000 times, open the parentheses, 1 plus 0.05 divided by 12. Okay, and then that caret, that's your exponent key. Now guys, if you choose not to simplify the exponent first, okay, and sometimes you might not be able to do it in your head, it's real important that you put it in parentheses. So if you want to put that 12 times 7 as your exponent, you need to put that 12 times 7 in a set of parentheses on its own. Okay, but if we type that all in and we're really careful about those keystrokes, what do we end up with for the amount in that account? $2,836.07. Okay, and the question is asked with a complete sentence, so we should answer it with a complete sentence. Okay, and your sentences, guys, they don't have to be elaborate. I'm not asking you to write an essay. All I want to know is answer the question, please. So, Rick will have $2,836.07 in his account after 7 years. Okay, and ask yourself, does that seem reasonable? So he's gaining about $800 in 7 years. Sounds a little bit more than we would expect, but keep in mind he's getting a 5% interest rate. And if you guys ever find a bank account or savings bonds that give you 5% interest rate, invest everything that you have, okay, because you're not going to find those accounts again. This is a really, really, really good interest rate. Most rates you're going to find are going to be like 1.5, maybe 2% on a good day. So if you find anything like 5%, put everything you have into it, okay, and then don't touch it. All right, number 2, Glenn deposits $7,500 into an account that gives 1.9% APR, much more realistic. Compounded daily. Not including leap years, how much money will be in the account after 6 years if there are no other transactions made? Okay, so the no other transactions part, guys, that's really, really important. Okay, the fact that he's never taking any money out, never putting any more money in, obviously those would change the final amount. So, got a formula, write it down. Okay, list the variables. Okay, and let's pick those pieces out of the story. So the amount at the end, that's what we're trying to find again. But what about the principal? How much is he starting with? $7,500. Okay, what about the interest rate? 1.9%. But, and what's that going to look like as a decimal? 0.019. Good. Okay, N. What did N represent? What did we say N represents? Cycles per year. Okay, and how many compounding cycles per year do we have here? 365. Okay, it's compounded daily, 365 days in a year, except for leap years. Okay, and T, that's how long it's been in there. And it has to be in years, 6 years. Okay, now we have all the pieces. Everything is clearly laid out for us. We can sub everything in. Okay, so we'll have A equals 7,500 times the quantity, 1 plus 0.019 over 365 raised to the 365 times 6. Okay, we've got everything written out. And guys, it's really important before you run to that calculator, make sure that you write out the formula, that you list all the variables, that you have it written out with those variables subbed in. Don't trust the calculator to do all that for you. Only trust it to do exactly what you tell it to do. Okay, so type that in. And what do we see about how much can Glenn expect to have at the end of those 6 years? What do we got? Good. $8,405 and how many cents? Probably 62. So he's got a lower interest rate, and he's getting about $400. Nope, excuse me, about $1,000 in 6 years. Okay, so answer me this. He spent less time accruing interest, and he ended up getting more than Rick did. And he's got a lower interest rate. How'd that happen? Very good. He started with a larger principal. Okay, so a significantly larger principal. So yes, that is reasonable. So we'll say Glenn can expect about $8,405.62 after 6 years. Okay, circle our final answers. All right, take a quick time out here, ask some questions. All right, back to it. Let's look at, flip over to the back and let's look at 3 and 4. I guess not flip over to the back for you guys. But how much money should Daryl deposit into an account that pays 6% interest compounded quarterly if he wants to have $9,000 in the account after 10 years? Okay, so it's a similar formula, or it's the same formula. A equals P times the quantity, 1 plus R over N, all raised to the NT. Okay, and I want to list all of those variables. And I want to assign values to them, at least to as many as I can. Okay, so A is the amount in the account at the end of the time. Okay, this time, Daryl wants to have $9,000. That's how much he wants to have. The principal is the starting amount. And what's the starting amount here? This is our unknown. This time, this is the one we need to find. Okay, they're still giving us everything else. What's the interest rate? Okay, 6%, but 0.06. Okay, what about N? N is the compounding period per year. If it's compounded quarterly, what did you say, Jordan? 4. Okay, and what's T? 10 years. Okay, so we'll take all those pieces and we'll sub them into the formula. Okay, so what's that going to look like when I sub those all in? Bridget, can you sub those in for me?
4 times 10.
There we go. Good. Okay, so this time, guys, we're looking for the variable that's in the middle of the equation. Instead of it being all by itself on one side, you've got to get it by itself. So, before we run to the calculator and start pushing buttons, do a little bit of algebra on the paper. Okay, this P is getting multiplied by all that stuff. So what am I going to have to do to get P by itself? Divide by all that stuff, both sides. Okay, and then I'll have P all by itself. And I'll have P equals 9,000 divided by the quantity 1 plus 0.06 over 4, the quantity raised to the 40th power. Yes. Now, if you can manage doing that in your head. Now, most of us guys, I'm not going to be super comfortable we're not going to be super comfortable trying to do all of this quantity in our head. If you are, great. If not, that's okay. There's a trick we can use on the calculator. Okay? I want to do all this and then divide 9,000 by it. Okay, but typing that into the calculator might get a little tricky. So we can use one of our exponential properties. Okay, so what I want you to do, guys, take this section, this piece right here that we want to divide by. Okay, work that part out. Okay, the 1 plus 0.06 divided by 4, all raised to the 40th power. So go on the calculator and go ahead and do that part. Okay, and what do you get? 1.814. Now, leave that number on the calculator. Right now, that number is on the top line of my expression. I need to move it to the bottom line. Don't we have an exponential property that we can use to move something to the bottom? A type of exponent we can use to move something from the top of an expression to the bottom? Negative exponent. Now there's a button on the calculator that looks like this. X to the negative 1. Okay? Push it and hit enter. And you should have something pretty close to 0.5. Right? Okay? Now take that, leave that number on the screen, and just do times 9,000. Okay, and about how much should Daryl deposit? Sorry, say that again? Good. $4,961.36. Okay, so complete sentence answer. Daryl should deposit $4,961.36. Okay? All right, so we have a formula. And anytime we're going to use any formula, we write the formula down. We list the variables, including any amounts we intend to sub in, and then we substitute those values in. If we have to solve for the variable, we solve for it. If all we have to do is simplify the one side of the expression, well, the one side of the equation, we can do that just as well. Okay? Just make sure we're given a complete sentence answer, and make sure we're asking ourselves if that solution makes sense.